In this section, we are going to discuss the acidity of phenol and substituted phenols. But first, let us recap the relative acidity of alcohols compared with water. In the previous section, we have discussed that alcohols are weaker acids than water. And the reason for this is that the conjugate base of alcohols, which is known as the alkoxide ion, contains the alkyl group which is bonded to the oxygen atom, which bears a negative charge. And this alkyl group exerts electron-donating inductive effect, which will intensify the negative charge on the oxygen atom. And when the negative charge on the oxygen atom has been intensified, it results in destabilization of the alkoxide ion, but no such effect exists in the hydroxide ion. So since the alkoxide ion is less stable than hydroxide ion, alcohol is a weaker acid than water. But when we go to phenols, phenols are actually stronger acids than water. This is because in the conjugate base of phenol, which is known as a phenoxide ion, the O atom, which bears a negative charge, the p orbital on this O atom will overlap with the pi electron cloud on the benzene ring, as shown in this diagram. So the negative charge on the O atom will be localized onto the benzene ring. So essentially, this electron density on this O atom is so-called spread out amongst not just the oxygen atom, but the 6 carbon atoms in the benzene ring. And because the negative charge is spread out, it results in dispersal of the negative charge on the O atom, and this makes the phenoxide ion more stable. Whereas no such dispersion of charge exists in water, which makes phenol more acidic than water. When we have substituted phenols, the acidity of such substituted phenols depends on the nature of the substituent, whether the substituent group is electron withdrawing or electron donating. So first, we are going to discuss electron donating substituents such as methyl group. When you have electron donating substituents bonded to the benzene ring, it results in increase in electron density in the benzene ring and will decrease the acidity of phenol. So for example, phenol's pKa is 10, but when I have a methyl group at the 2 position, it results in a higher pKa value, which means that 2-methylphenol is a weaker acid than phenol. This is because when we compare the conjugate bases of both compounds, the conjugate base of 2-methylphenol, the oxygen atom, has a higher electron density. So we mentioned just now that there's overlap between the p orbital on the O atom in the phenoxide ion with the pi electron cloud in the benzene ring. So it means that when your benzene ring is more electron rich, correspondingly in your phenoxide ion, the O atom will have a higher electron density. And this increase in electron density in the conjugate base of 2-methylphenol makes the conjugate base of 2-methylphenol less stable than phenol, and in turn it will make 2-methylphenol less acidic than phenol. Whereas for electron withdrawing substituents such as Cl and NO2, it will have the opposite effect. They will decrease the electron density in the benzene ring and make the phenol more acidic. So you can see 2-chlorophenol and 2-nitrophenol, both of them pKa value is smaller than phenol. And the reason is also opposite. When you have electron withdrawing substituents, so for example, when we compare the conjugate bases of 2-chlorophenol with phenol, the electron density on the O atom will be lower in the conjugate base of 2-chlorophenol. And this makes the conjugate base of 2-chlorophenol more stable than the conjugate base of phenol, which makes 2-chlorophenol more acidic than phenol.